Good morning or good afternoon, everyone. Welcome to our webinar. Thank you for attending and being with us. My name is Pınar Afşin, and I am the R&D Executive of Polytechnic Metal, which is the Light Metal R&D Center of COVENTYA Group, and I will be your host today. In some minutes, I will hand over for our presenter, Can Akyil. He is going to talk about coloring of aluminum. Probably many of you know COVENTYA. However, who may not familiar with, we would like to briefly introduce to COVENTYA. COVENTYA is one of the biggest surface treatment chemical suppliers in the world, and COVENTYA has a long history dates back to 1927. However, COVENTYA names was born in year 2000. The growth strategy of COVENTYA have always been in strategic add-ons, both in terms of geography, but also technology. One rather recent event was the acquisition of Politeknik in Turkey 4 years ago, where COVENTYA took a large strategic step into complete harmonized range of aluminum surface treatment product catalog. Our activity is related to large variety of markets and business. Almost every application of metals or parts or end user products needs some surface treatment. It could be corrosion performance, appearance, functionality, so on. Therefore, our activity serves an important role in the whole manufacturing chain. This is another view is also the different product segments for how we divided our activity in different segments of the market. From our different market segments, the automotive segment is one of the key industry where COVENTYA pays attention, certainly. Not only due to the complexity of car, but it's also one of the largest markets for the manufacturing industry, and the surface treatment plays a key role in several different aspects, all from the corrosion, aesthetical, or functionality. One reasoning behind COVENTYA's strategic approach into ASC can also be explained by the development into e-mobility. One of the challenges in e-mobility by electrolytic storage in batteries, which is really heavy. So this weight needs to be compensated in the role of construction to overcome challenges in the range and performance. To overcome such challenges, the usage of light metal, aluminum, magnesium, and carbon fiber increases day by day. Additionally, sustainable aluminum offer a great possibility to reuse. For your information, there is a possibility to ask questions in the toolbar to right-hand side. We will try to answer your questions after the presentation, depending on how much time we left. Now, I would like to welcome this gentleman next to me, Dr. Akyil. He is a PhD in electrochemistry. He is also Managing Director of Polytechnic Metal. Can, please go ahead.
Thank you, Pınar, for this nice introduction. And let me continue with this introduction of explaining a little bit more in detail what we do have or offer in terms of aluminum surface treatment. For sure, after the acquisition to COVENTYA Group, our focus have widened or broadened from architectural to automotive and also aerospace. Also, the footprint that was possible to obtain with a global company has enabled us to take part in many organizations such as AAC in the United States, IED in Turkey, FAO-A, ADAL, or ITAL in Italy. And we are providing our chemistries that are Qualinote or Qualicoat approved in almost all the countries that have a aluminum surface treatment. And you can see wherever, as Mrs. Afşin has mentioned, wherever there is a production site of an OEM, COVENTYA has not only a warehouse, but also a expert laboratory and a production site. So now we have mentioned heavily on the importance of aluminum. Let's talk about why aluminum is important, because quite frankly, it has one of the best weight to strength ratio. So it's lightweight, ductile, soft, it's not brittle. relatively low cost, non-magnetic. So it has many desirable properties that is enabling it to be used as the most used non-ferrous metal in various applications. But it has one big deficit. That is its amphoteric nature. That means it will get corroded under alkaline or acidic media. Therefore, it needs a surface protection. There are two big families of more commonly used surface protections for aluminum, and they are basically anodizing, which we will talk very much in detail today, and also conversion coating, and then powder coating process. So in our previous presentations, we have touched bases with anodization of difficult alloys, cast alloys, which was our newly developed patented process cast alloys. And now we have talked about the 557, or soon to be Qualinode approved anodizing additive to improve your performance in anodizing and improve the reproducibility of the results. Then we have Mr. Per Alsten have discussed in detail the pre-treatment aspect of anodization and also the pre-treatment of conversion coatings, why they are important and how much difference can be made in terms of process stability and reproducibility of the results. Now we will continue with our next step of our webinars, which will include one of the most challenging aspects and most challenging processes that you have in this surface treatment of aluminum, which is the electrocoloring. So briefly, let's recap what is anodizing, because we're going to use this terminology a lot so that we are all on the same page. Per definition, anodization means loading the surface anodically or charging it, which means dissolving basically aluminum and growing the inherent oxide film, which is about 3-5 nanometers thick, to several microns. And this is something very interesting because you're basically dissolving aluminum by applying an anodic current, and it really, instead of getting plated, it is converted to a porous structure. And this porous structure is very beneficial, not that it is transparent, but the most important part of this porous structure is that you can use this as a template for several applications, even growing for nanofibers, but in our case, for electrocoloring, you can use this to precipitate several metal salts in order to change the surface aspect or surface color. So the reason why anodization is a very desired coating process, or the most common surface treatment for aluminum, is that it has many desirable quantities or qualities. It is glass-like. Basically, aluminum oxide is the second hardest material that can be found naturally without synthesis. And by converting the aluminum to aluminum oxide on the surface and anodize the surface, you can get practically a very hard, transparent coating that is a part of the surface because it's converted from the aluminum. Therefore, it will not chip or peel, or it's not subject to filiform corrosion. But today we will also touch base on the metallic appearance because it is a transparent structure. It stays as metallic. So therefore, what happens is the surface can be colored without changing the metallic appearance, which is very important for aesthetical application. So by itself, anodization has been patented in 1911, and it's very straightforward electrolysis reaction. And I always say, and people disapprove at the start, is that you can do it in a small bucket with a car battery. Well, in reality, you need a much more complex system in order to keep the parameters in the bath and in your production line more controlled and more distributed homogeneous. And it is very important because anodization, it's not a plating, so it is a conversion coating, basically. So it is very dependent on the parameters. And these parameters that are subject to individual processes are not affecting only this process. But because these processes are the precursor for the other ones, what happens is you do not have about 100 different parameters, as you can see here, but it's more like 10 over 10, which confirms the saying there is about 1 million things that could go wrong with the anodization. So the complexity and the need to control these parameters is paramount, because it's a conversion, and the way we convert the aluminum, which is present on the surface, to the aluminum oxide determines all the attributes that we talked about, like corrosion resistance, hardness, wear resistance for us today, which will be very important, color homogeneity and shade, and also metallic appearance, because quite frankly, all of these attributes, they're a function of how these pore structure and these individual pores are distributed throughout the surface, because we are using them as a template, for instance, in our case for coloring, in order to precipitate the metal salts. So the more orderly they are distributed, the better the color homogeneity is going to be. So therefore, we take a very high, or we give a very high importance to how these layers or how these pores are structured or constructed, as you can see here. And in order for us to be able to visualize this, I like to use this analogy with the fire triangle, where you have your substrate and it is limited. So whatever is your substrate, or whatever it doesn't have or has too much, you will have to compensate throughout your process with the parameters you use, and utilize your process in order to be able to construct the right surface, the right oxide structure that you need for your application with the right desired properties. Therefore, we are taking this approach from the plating side, is that whatever you have or not have on your substrate, it will be possible to condition by adjusting your substrate in a chemical manner. So therefore, we do not just single out the processes like anodizing or coloring, but we, like we have shown with the fishbone diagram, we like to use the entirety of the process in order to give us more room to be able to apply the parameters that are needed to structure the oxide layer, and also adjust the substrate so that we have a much more suitable base to grow these oxides. So, and if we look more closely, you can see the pre-treatment aspect will be related more conditioning the substrate, and then anodizing and coloring for our example, or for our presentation today, will be more guided through to the electrolyte and the parameters that are applied in anodizing and coloring. So therefore, we will be segmentizing or we will be distributing the presentation according to these three processes that have a big effect on the end color, on the end appearance of the part. So when we also look more closely, why, for instance, anodizing is very important for coloring, is that, as we said, because we are going to be using this as a template. And in reality, it is very important to have these pores structured or distributed throughout the surface, like with these honeycomb-like structures. So, and then we have the right template, which means the right structure, where by using pulse or AC or even AC-DC type of a current, we can start precipitating the right metal salt with the right amount in those pores that will give us the right color, as you can see here. So the coloring as a process, if we look more closely, is actually a very complex process. So we have our metal salts or metal oxides in our bath, and we are applying a alternating current to our template, to our aluminum substrate, and these metals, they start precipitating out at the bottom of the pores under the influence of this alternating current. And there is a battle or constant balance between the solution, the acidic solution that we are in, to precipitate or dissolve, again, the metal salts that we are precipitating in the pores, and the current that is trying to precipitate a higher amount, as you can see on the right-hand side, into the pores in order to change and adjust the color. And when we look a little bit more closely, what happens throughout your process is that here you can see on the left-hand side is the start of the process. So you have a minimum amount of tin. These belong to the tin sulfate-based electrocoloring process. So in maybe 30 seconds or 45 seconds, you have almost 500 nanometers or 0.5 micron thick tin precipitation, which is barely visible, and you have a very light color. As you can see, the L value of the color is around 65, so it's a light champagne. So the time goes on, you see that the amount of precipitation in those pores is increasing, but it is not increasing in the same speed and efficiency. So therefore, as you can see, the more time goes on, it's just like boiling water. Getting to the black is more challenging than to getting to dark brown. So as a rule of thumb, increasing the coloring time not necessarily, or even the voltage, not necessarily changes the shade itself, but more changes and affects the amount of deposit, which in return makes the surface or makes the transparency of our oxide film less. Therefore, more light is absorbed and we get to black. Well, I know that this is another question, that how can we change the A and B color or A and B values? So how can we change or shift the color a little bit? Quite frankly, the color or the shade A and B values are more affected from what you're precipitating. As we can see here, this is copper sulfate based chemistry, which has a reddish color, rather than it is affected from the coloring parameters by themselves. They do change the shade or hue, and it will create, or sometimes can create, huge problems. But to make a drastic change from reddish hue to bluish hue, you need to use a different chemistry. So now I have been explaining a lot of technical details, technical explanations, but the question remains, what about the title of this presentation? I mean, what is the problem with matching control samples or matching customer samples? So this is our actually a simple, I would say simple schematic of our lab, and how happy they are to receiving customer samples, because I know that many of you doing professionally anodizing, producing your own samples, it's not the most challenging thing, because you make your color spectrum and you continue on according. But whenever you're receiving a sample that you need to match, just like we are having it every day, then the life becomes quite difficult, because it's a big challenge to be able to match one-to-one a color that has been done by someone else on a different part. And quite frankly, as a rule of thumb, it is easier to produce a darker color on a very low gloss surface, or it should be, and it's much more challenging to try to match a color that is produced on a very glossy surface and has a light shade. Well, in reality, this is what happens. So you get two samples, you're trying to match them. Although supposedly the profiles are the same, you have slight variations and you're slightly above the limitations with the delta E. So in reality, this is a normal life for our lab, for Pinar. So it makes her unhappy, so to speak, because even trying to match black is a big challenge. So therefore, when we were discussing how can we present or how can we explain the challenges in electrocoloring, we said, well, we are having these challenges every day, and for us, the biggest nightmare is match me if you can. And you know what? It gets even worse. We have another, you know, type of request. This is coming from our customers, and it is a little different than match me if you can. It is help me if you can, because they try themselves to try to create the color, and then they end up with same profile, same type of profile, same math, but almost a completely different color. And then we are in the lab, we are cutting those, we are investigating. This is a SEM picture, and you can see that the anodic oxide layer is almost the same, and also the precipitation, which makes our life even worse. So this is normally, the previous picture was like this. This is what's supposed to be, and this is where we end up. So match me if you can, and also help me if you can. Therefore, we would like to go right now a little bit more in depth why these problems are occurring and where does this inconsistency or the challenge on coloring or matching the samples or even creating reproducible results with expected or with anticipated color schemes can be obtained. So for that, we need to dig a little deeper how the color physically, how the phenomenon which we call the color is actually produced. There are three ways for the color to occur. One of them is the transmission. So if light travels through a media that has a certain color, some of the wavelengths will be absorbed and the remaining one will appear to us as color. The second one is reflection. This is more for metals which have free electrons in their Fermi levels. So the light will interact with those electrons, and whatever is reflected back will have this metallic shimmer, so to speak. And this is what we call the metallic appearance. And the last one is, in many of the cases, the insulators, so like or the organic ones, which do absorb a big portion of the incoming light, and only a couple of wavelengths they return, which then we perceive as color. And in order to measure the color, as we have seen, I know many of you know already that L, A, and B values, but it's always good to see them in this Cartesian diagram of colors. So A represents from red to green, B represents from yellow to blue, and L is basically a number or the indicator for how shiny the surface or how much light is coming back from the surface. If L is 0, then no light is coming back, so therefore you perceive as 0. Hence, you start with a normal aluminum with a very bright surface, and then you end up with the precipitations, less reflectivity, less transparency, therefore you end up with black. So you can see here the color and the generation of the colors is strongly related to the electrons and how the light is also absorbed or transferred or reflected back. So in our case, unfortunately, why this is so challenging and why we are having these problems is that when we do anodizing and when we do electrocoloring, we are creating a matrix, or we are creating an ecosystem which basically generates color. I mean this because first thing is the incoming light, it is reflected back from the seal layer or the metal precipitate or the anodic oxide by itself, which creates a color. But it gets more complex because then we have the underlying metal, the base, which again reflects some of the light which is going through the transparent oxide layer, which is good, but the incoming light is also changed by the oxide layer. So we have transmission, we have reflection, and we have absorption. So it couldn't be more complex. Therefore, there are many parameters that is affecting the coloring phenomenon. But I like to use this analogy of brake lights, where the base metal, the color of the oxide film, the type of the metal salts, they all have a huge effect on what type of color you're going to get, which makes the system very unique, but therefore very complex and hard to control if you're not categorizing the problems that you're getting on the line. On the line. Therefore, for us, matching a sample starts with definition of the problems. So when we say definition of the problems, it is much easier to group them, because the famous question, how can you eat an elephant one bite at a time? So because it's such a complex system, you have to diversify, divide, and group the things that are more relevant. The first group is related to the base metal. So the alloy, what type of surface treatment it has been gone through, is it casted or forged? And then the second part is related to the surface texture, because these are basically determining how reflective your underlying metal will be. That will be eliminating your oxide layer and the precipitate. Secondly, is related to the anodizing and also coloring processes, where the transparency and the orderly or homogeneity of the oxide layer will have a huge effect. And finally, the third group is related to the coloring chemistry. So we have talked about anodizing as a process, but let's dig a little bit more deeper in electrocoloring as a process. Okay, we talked about these groups, and it's much more easier to put this fishbone diagram and understand what are we dealing with and what can we do. So the first group is related to the base metal and surface structure, and also strongly related to the conditioning of the surface, where we can do a lot of things in order to make it better with the pre-treatment. So we said we were having problems with sample A and B. Although we have almost the same anodizing and same coloring, the resulting color was very different. And when we said it was very different, we started off stripping the layer and then looking underneath, or what is happening, and we realized that the gloss was completely different. Therefore, the sample A had much more backlight or illumination coming from the anodic oxide, which was making the color appear much lighter. Therefore, the L value much higher, although A and B values are very close. So same example, the backlights are dark red. As soon as you hit the brakes, you get the lights coming up. Therefore, the color appears much lighter. So same example, what can we do in order to have a better underlying substrate or a better layer is, quite frankly, easy, or relatively easy. The topic of Mr. Per Alsen. So we need to have the right substrate and the right surface with the right roughness and also distribution of the alloy, so that we have the base, which is uniform and much more suitable to grow our anodic oxide, which will be then the template for our coloring. So here, as we have discussed in our previous webinar, we have many alternatives. One of the most common ones is using caustic etching in order to get rid of many of the unwanted alloying elements and have the right smoothness, right roughness of the surface, right gloss of the surface. But the caustic itself is a limited process, where changes in the alloying elements and the changes in the production cycle will create a lot of problems. Therefore, we like to use more compact and more flexible processes like we have introduced, especially if we are thinking about not only the extrusion process or the forging process is going to change and make the microstructure much more inhomogeneous, but also the alloying elements, meaning different series of aluminum, but the use of, which is a hot topic today, the use of recycled aluminum, which is increasing the silicon and iron content, will have an effect on the color. Therefore, as we have previously suggested, it is much more complex, it is much more flexible when you have a process like we have introduced the caustic free mat, where you can adjust the surface gloss and also adjust the alloying elements distribution on the surface. Therefore, by using these approach and evening out the surface and making it exactly the same by removing some of the unwanted intermetallics, by removing the grain boundaries, and then finally by etching the right amount, you can basically get exactly the same color, making our very unhappy team to just a little bit more happy, because you see that we have still 2 more steps to go related to anodizing and then related to coloring chemistry, which hopefully at the end of the day, I see that Ms. Pinar will be smiling again. Okay, now we have our second group, which is related to the oxide layer structure and the distribution of the oxide layer. As you can see here, the anodizing cycle will be very important in order to correct these problems that are originated from the oxide layer. So the anodic oxide and how anodic oxide is constructed or converted on the surface will be a key parameter in how our color is distributed and how our color is perceived, because the way we construct the anodic oxide, as you can see here, this is the thing that everyone wants. Beautiful honeycomb-like layer structure. They are distributed evenly. That means we have a very good distribution of our pores, metal salts, but also a very transparent layer with minimum integral coloring, which means with minimum discoloration of the layer. Well, in reality, as we have discussed, this is what we want to have, but very seldomly we have a layer like this. As you can see, in general production, this is one of the reasons why there are many deviations in between colors, is that you end up with a surface like this, which has many defects. And when you dig a little deeper, this was the subject of our webinar about the 557, please check the link, is that especially at the start of the anodizing process, although by itself it's relatively easy, how the oxide layer is growing, how it starts, it's very chaotic and complex. And all of these defects, they're appearing at the phases 1, 2, 3, which is happening very fast. And they are mainly the causes of these defects, where you can see the alloying elements. This is a little more exaggerated, so to speak. And this was the subject of our Castellox webinar, where you can see even 12% silicon. And on the picture on the right hand side, you can see that with 10 or 9% silicon, not only you have a inhomogeneous oxide layer, but it's very hard to grow a homogeneous oxide layer. But today we are more talking about, because we are talking about electrocoloring, rolled alloys, which are extremely pure compared to castings. But even with them, we are having a lot of problems and a lot of discontinuities, especially if we consider that in future there will be more recycled materials used. So therefore, we will have to do something about it. And again, returning to our example with the black, the more alloying elements you have, the more changes in the production cycle you have, and also the anodizing, even which is supposed to be easiest color, the black, you're gonna have problems. So this was our part of our webinar with about the 557. So in order to control the growth and the distribution of these oxide layers, it is paramount to control the anodic oxidation cycle. Therefore, you need to control not only the voltage or the amperage, but quite frankly, the speed in which the anodic oxide is growing. And there, because you're going to have a subsequent coloring process, the productivity in time is very important. And under pressure of the production, it is very important to have some additional additives that widens your operating parameters. And this was a real life example from one of our customers, So because he had problems, or they had problems with their production, what happened was they needed a speeder or faster anodic oxide cycle. But it was creating a less deep black, because quite frankly, the pores were not as uniformly distributed as you can see here. And even on the left-hand side, you can see that the pores are deviating to left and right, causing this rainbow-like structure. So on the right-hand side picture, you can see that by using the 557, controlling the anodic oxide cycle much better, you can get a more deep and more uniform distribution of or precipitation of tin-based electrocolored agent. But more importantly, we have briefly mentioned that the distribution of the pores, yes, they're very important for the homogeneity aspect of the color, but they're also very important how transparent your anodic oxide will be. Because if those pores are not orderly distributed, the oxide layer, it will not only be transparent, but it will be opaque. Therefore, the color that you're gonna get, or you are going to perceive, will be much dull, and it will be different. Therefore, it is paramount not only controlling the anodic oxide parameters or anodization cycle from in terms of how orderly these layers are growing, but how transparent your layer is going to be with the right production speed. Therefore, it is paramount to control the oxide layer, and also have the right basis material. So right now we have our basis material that we have adjusted or conditioned with a pretreatment. Then we have grown the right oxide layer on top, which gives us the right template. And here, by doing these, you can at least say our lab is quite happy. They're not very happy, but at least for black samples, for dark and not very shiny samples, they can assume or anticipate what type of color they're going to get. It's not a guessing game anymore. But okay, we talked about black and matching if you can, but it was not related to only black. Now, let's go to the most challenging part, which is the problems that are related to the coloring chemistry. What can be done in order to make it easier for you to match the colors or the test samples and make the life of our lab team a little bit easier. So here, I would like to return to this graph where we talked about, okay, dark colors and low surface gloss, because quite frankly, almost no light is coming back to us. We do not see any defects, and also we do not perceive any difference. But still, there are many parameters that are affecting the surface. And in terms of color reproducibility, also the light color and high surface glosses are not very easy to control. Quite frankly, the reason is, you can see here, we talked about the balance between the electrolyte that is trying to dissolve whatever you're precipitating in the pores as soon as you're switching off the current. So if you have more, like in the example of black, about 15 microns of precipitation, and you have a much broader window in almost 100 seconds in order to adjust your black, it's a much controllable process. Whereas you can see with the light shades, you almost have nothing, and even the smallest difference from 0.55 to 1.5 changes the color of the surface drastically. So not only the problems that are occurring with light shades are coming or originating from the base metal or the oxide layer structure, but they are also strongly related how much precipitate you're having or how much metal salt you're having in your pores and how well they're distributed. So therefore, it is paramount again for electrocoloring or reproducibility of the electrocoloring to separate what we're going to do. Like for dark shades, we are expecting something else from the system. That means process time. You don't want to be too long in this process, the precipitation efficiency, and then adjusting the parameters. So it is fairly easier as long as you are adjusting the other two prerequisites or the precursors, which is pre-treatment and the anodic cycle correctly. So then you can end up with a happier team as long as you're making a dark color and a lower surface gloss. But as we have briefly discussed, because we have very small amount of precipitate, that means we have a very narrow margin of error. Therefore, for light shades, we need to do something else because there are other players involved in this or affecting our performance, making our life harder. So here we see a much broader effect of the AC ramp, DC cycle, stabilizer amount, process temperature, process time, even the rinse bath. If you leave your profiles too long in the rinse bath, the color will be fading out. This is one of the biggest problems that you're ever going to face with light champagne colors. Therefore, for lighter shades, it is not enough to get these pre-treatment and anodic oxide cycle completely perfectly in line, but you need to do and control the coloring. Therefore, it will be much more important to have a chemistry that would enable you a lower deposition rate, hence sacrificing the chances of getting the black, but therefore a longer process time in which you can control the AC cycle, DC cycle, and also the deviations that you would have with a fast process. So in order to demonstrate this to you, we have devised or we have structured the test. So you can see here at the stage 1, we have conditioned the surface with etching and also brightening so that we have with all the samples, the same gloss, same surface, and same distribution of the alloying elements. Then we have done exactly the same anodizing cycle with the stabilizer in it. Then we have applied different coloring with nickel-based, which is the aluminum steel 885, and then aluminum color 890. And finally, they were sealed with the same system so that we can start testing the stability of color. So what happens is that we wanted to show you the deviations. So we have done all colors that we were asking for at least 3 times or 4 times so that we can show you the deviations in terms of L and B values and show you the delta L and the stability of different systems. So here you can see with the team-based coloring, as soon as the time of the process is increasing, therefore the darker colors, as we have seen, they're much more stable in terms of delta E, whereas the lighter the shade, the worse it gets, and you have much more deviation because, quite frankly, it is a faster process. Like here for very light champagne, it's only 22 seconds. So what happens is we were talking about 8 micron of precipitation for dark bronze or 15 micron. We are talking here about nanometers, and they're affected almost about or with everything. Hence, you can see that even a small change, about 6 seconds or 10 seconds, changes the L value from 70 to 40. So that's a huge change. Therefore, you need to be very careful about how this process is going on, and let alone making the same color on the same parts. We are currently trying to match someone else's sample. Therefore, it is paramount that we choose the chemistry and the coloring parameters accordingly so that we can match the sample. And here what we have proposed is a nickel-based electrocoloring, which we call aluminum steel 885. So not only we are talking about right now light champagne, but we are talking about colors. They are very similar to stainless steel. Quite frankly, the main reason is this is a very low precipitation process. And because it is a very low efficiency precipitation process, you end up with a longer time even with light shade, which enables you control your process, quite frankly, almost perfectly. You can see here. And although the amount that we are precipitating here again is for stainless steel color, so it's even lighter shade than champagne, close to 100 nanometer, it is much more controllable because, quite frankly, the time you need is almost 2 minutes, and the change in L value or the precipitation from 120 seconds to 250 changes not drastically. Therefore, yes, you can never get the black with this system, but it gives you much more wider range so that you can adjust the color accordingly and you can get the repeatable results. As you can see here, the change of thickness, the change of precipitation amount changes, but it changes much more docile, it changes much more controllable. So, of course, I could say that by using the right chemistry, the right surface conditioning, with the controlled anodic oxide cycle, by using the additives, you can get or meet each color. Well, the life is unfortunately not as perfect, and I would be lying that it will solve all your problems, but it will at least solve all your problems related to darker shades, even they are on brighter surface. And this approach, this system, where we are thinking about this whole coloring process in conjunction with pre-treatment and anodizing, will give you a higher color reproducibility and also a happier lab team. So, as conclusions, we know that anodizing or the performance or the shade or the color of the surface is influenced by manufacturing. And not only that, it's very complex because, as we have seen, if something changes with the pre-treatment, the color of the profile could change completely. Or if the anodic cycle is not done correctly, or if you're speeding up too much, even with black, you can have problems. Therefore, you need to get these two perfectly in line so that you have a chance in coloring in order to match the color or get the desired color. But even that's not enough, because even if you're applying the perfect entry to the coloring phase, the parameters that you're going to adjust or you're going to apply in coloring cycle will determine the shade and the hue of what type of color you're going to get at the end of the day. So therefore, it is paramount to separate the problems that you're having on the line, or it is paramount that you look at the profile that you want to match by separating the problem sources. So you need to verify what type of underlying metal there is. Is it forged? Is it casted? Is it machined? And then the alloy, the heat treatment, so that you know what type of basis you have. Finally, you also need to understand what type of oxide has been applied so that you can decide what type of color you should choose and apply as a process. So therefore, it is paramount to use not only anodizing or pre-treatment, but use a combination of these in order to adjust your substrate and then create the right oxide film on which or in which you can precipitate your coloring agents. And by applying this and even choosing the right electrochemical process, like the selection between nickel and the tin, as you can see here, for lighter shades, the nickel-based process is much more suitable because it is, quite frankly, a more docile and less speedy process where you can have more consistent results, but it will never be possible to get to black with this system. Whereas for black, you can or you should choose the electrocoloring with tin beds. So by applying these parameters, you can switch your team from this or make their life much easier when you can differentiate between what type of metal we are dealing with, what type of surface we have, what type of anodizing needs to be adjusted. Finally, choosing the right electrocoloring chemicals will make the life of you, your team, and also your customer not perfect, but it will limit the deviations between colors and also the hardships of trying to do electrocoloring. Thank you for listening to us. Please do not forget to follow us on social media. We're a very active company in terms of trying to notify you, especially in these difficult times where we have COVID. We cannot be there personally, but at least we can update you about the recent developments of our chemicals, of our new processes, technologies. So I will leave this presentation's control to Pinar for further Q&A. Again, thank you for your attention. Okay, Pinar, go ahead.
Thank you, Mr. Akyil, for this nice presentation. Before we continue with the questions, I would like to remind you and invite you to our next webinar, 10th of June. We are going to talking about sealing. So please check the hands-off section on your control panel. So let's continue with the questions. The first question about the stabilizer. Should a stabilizer using the tin-based electrolyte? If yes, is there any possibility to analyze the stabilizer?
For sure. There are several ways to approach this question. There are two types of stabilizer. One, and it's very important to differentiate. One is stabilizing the bulk solution, so tin sulfate itself in the tank. And the second part is stabilizing the coloring process. So the stabilizers that we are offering to our customers do both, and also the products that we are proposing, the 980, contains a big portion of that stabilizer. But still, the stabilizer is needed to increase the throwing power of the chemistry so that you can have more uniform results. So this is the first section of the answer. And the second section is, it is very important that you can analyze this. And yes, we give great value and importance that you can monitor the changes in the stabilizer content, and you can adjust the stabilizer accordingly, because quite frankly, this is a very delicate process. It's not, I wouldn't say it's hard, but you need to be wary of the problems that could occur. And stabilizer is one of the things that we can use to compensate some of the problems that are originated from the previous processes. So therefore, we use, it's not a must, but we like to use or offer our customers stabilizers that are possible to analyze.
Thank you. And the other question is, could you please give more information about the copper-based electrolyte? What is the achievable colors?
For copper, although the black is going to be a little problematic according to Colonel, still copper is a even higher precipitation efficiency process. So you can get easier or even faster to black by using copper. And all the other colors that are possible to achieve with copper are or do have the inherent redness or orange color that copper has, because quite frankly, you're precipitating instead of a tin salt, which is more yellow to dark blue color, and the more you're precipitating, you're getting black. So therefore, the colors are changing from champagne to black. With copper, it has, or its oxides are more reddish to orange. So therefore, the colors will start with pink, go to rose, and then finally you end up with black.
Thank you. The treatment times that you present is shorter than what we have in our line. What is the reason for this?
Okay, good question. Electrocoloring, we talked about the precipitation efficiency. Anodizing is a conversion process, so therefore it is much more forgiving than the coloring. Therefore, when you're doing a AC coloring or electrolytic coloring in your lab, what happens is that the amount of the ratio of anode to cathode plus the distance in between them does make a huge difference. Therefore, when you're doing a lab sample compared to a big architectural anodized line, the times almost goes 3 times faster. So this was our pilot line. I would say somewhere in between. Therefore, we know as a rule of thumb, when we are matching customer samples, when we send out a recipe, which is a daily business for Ms. Pinar, is that we warn our customers the voltages that we apply are maybe a couple of volts lower, and also times are at least half shorter. Say when we say 6 minutes, you would end up with about 12 minutes. And this has a lot of things to do with the ratio of anode cathode and the distance with anode and cathode. I hope I didn't do any mistake. I mean, you know better than me. It's
Perfectly
your
correct.
belief right now.
No problem at all. What is the chemistry that precipitate at the pore bottom during the electrocoloring process?
Well, is it your question or coming from one of our customers?
No, directly coming from one of our listeners.
I know, and this is one of the magnificent things that we are we or you have been lucky and also skilled enough to be able to demonstrate, and you were able to also win an award with that study, apart from master's thesis. Is that, well, it's a complex structure, and we are also doing more analysis on that. But whatever is precipitating, it has maybe 10 to 20% metal in it for sure, but the bigger portion is complex oxide. So it contains, when we are talking about tin hydroxide, tin sulfate, and even a portion of tin oxide, because of the complexity of the reaction. So it's not pure metal or it's not pure oxide. I hope it, because this is a normally, I would say, an hour-and-a-half presentation, only talk about what is precipitating and how is precipitating. And I believe you have 2 papers on it, so therefore trying to explain it in 2 minutes, this is as good as it gets.
It was a quite good summary. So maybe we can answer one more questions. There is a lot of question about the extrusion quality and alloying element relation with coloring. Is there any relation between the extrusion quality and coloring?
Of course. When you do the color, the first thing you realize that if you're doing the coloring on a mill finish sample, wherever those streak marks are, they will appear either darker or they will have a brighter color. And it's exactly the sample that we have shown, which were unevenly evenly etched. So again, the same goes for the alloying elements. Let me put it in a different perspective. Even if you do the same anodizing and same coloring on a 6060, 6061, 6063, and 6082, which was one of your recent problems, Mark, is you're going to end up with different colors, because quite frankly, they have different amount of iron in it, they have different amount of magnesium, manganese, silicon in it. So what happens is, not only the oxide that is growing on the surface, let's say we have the same surface roughness, the oxide that you're going to get will be different, therefore the sizes of the pores will be different. And when you apply the coloring, therefore the conductivity of the barrier layer will be different, hence the amount of precipitate and the incoming light or the color shade will be different. The question is it possible to match? Well, Pinar, I know that you can do that, but for that, actually our previous webinar about the pre-treatment is paramount. That means we do not etch the surface just to adjust the surface gloss or the surface roughness. The reason why we're using an acidic base and an alkaline base is, quite frankly, to remove some of the intermetallics, create a zone which is more rich in aluminum, so that you can grow a better anodic oxide. So is it possible to match? Yes, but you need to use the process in its full extent, which means including the pre-treatment, not just for cosmetic etching, but for, as we say in plating, for conditioning the substrate.
Thank you for answering presentation. I think time's up. So the rest of the question will be answered written. Thank you, join us, and we will hope to see you in our next webinar. Thank you.
Yes. Thank you for listening. And I hope you're all healthy and stay healthy until we can get rid of COVID. Bye-bye.
Bye-bye.